linear subspaces. One, lines. Lines are linear subspace having a single vectors as base. Lines is is any linear subspace of dimension 1. A line, say L equal alpha, no, let me call it lambda V, lambda in R for some V in V is the line passing through V. Let me draw it. Here we have my V here we have my V, and here we have the line through V. So let me call it LV. This in 2 dimensions. Then we have another important, actually fundamental for what it concerns us, kind of linear subspace are 2 hyper planes. So meaning linear subspaces of dimension n minus 1 for if n equal 2, we have a line. But in general, any hyperplane can be written as a set of all vectors orthogonal to a given vector. So it's characterized as a set of solution of a linear equation. Because orthogonality is defined through what? Through inner product. More solutions. And it's, if we are in R3, an hyperplane is a plane passing through the origin. That's basically all. Remember, all linear subspace contains the origin. In particular, as a theorem, all linear subspaces are vector spaces, meaning closed under addition and multiplication, and multiplication by a scalar. And indeed, it's an alternative way to define a linear subspace. But if you think geometrically, so this is a plane and it doesn't pass from the origin. It doesn't contain zero. So not a linear subspace. This is called an affine space. But try to think as we can obtain this plane. If you see, you can translate this plane. Let me try to find a good color. So my plane crosses the y-axis here in so this is a translation of a plane passing through the region. This is x. So this is y and this is x. But it doesn't really matter. So it's not very far from a linear subspace. It's not closed, perfectly closed. And in general, what is an affine space? Translation of linear space by a vector. So A is a linear, is A included in Rn is an affine space if there exists B in Rn such that